Hello, and in the next set of lectures, we're going to move on and look at something slightly different. Previously, we've concentrated on time series of river flow analysis. Here, we're now going to have a look at cases where we don't have any data for the site that we're interested in, and we wish to predict the size of floods for those sites. This is flood estimation for ungauged sites, sites where we don't have river gauging data. And in this first section, we're just going to have a look briefly at some of the basic underpinnings of some statistical approaches we can use to address this problem. We're going to look at an approach developed in the UK in something called the Flood Estimation Handbook, and we'll have a look at broadly how this works, and then we'll have a look at some examples of the predictive equations that we might use. So what we have in the map is really the basis for this approach. So we have Great Britain here divided into 10 regions with numbers, and this graph shows the flow divided by the mean flow in each of those regions for events from the 2-year flood, the 100, the 500, the 1000. And what we see is that in areas towards the west of the country, we tend to have these curves that are relatively flat. And then in the south and east, we have curves that rise much more steeply because different geology here is more permeable, there's more groundwater influence, and the terrain is relatively flat. In the west and north, the terrain is much steeper, limited storage of water within the soil or within the bedrock gives rise to different hydrological responses. So in 1975, the Flood Estimation Handbook came out, and there have been various iterations of that more recently. And what this allowed people to do was to estimate flood magnitudes from data that have been collected across the country. So you can use data from all across the country if you wish, but you can also choose data from what are called donor sites, which are sites that are hydrologically similar to the site of interest. They might have a similar catchment size, similar geology, similar soils, similar land use, and that means that you can compare the results from those donor sites with your site of interest quite reliably. If we don't have data at a site, it's what we call an ungauged site. We can download data, catchment descriptors, available for any catchment over half a square kilometre. This will be elevation, gradient, land use, soil properties, and other factors. And we can then use appropriate parameters to put into predictive equations, either from statistical relationships, or we can use a nearby gauged catchment and scale the parameters from that nearby site to the site of interest. If you want to see how this works, it's all explained in the Flood Estimation Handbook online. It's been updated a lot since 1975, but the structure is broadly similar in that we start by asking the question, do we have data at the site of interest? If so, we'll go down here. If not, we need to estimate the characteristics of our site of interest from the catchment descriptors at our subject site, the site we're interested in. Do we have a suitable donor site? Is there another place nearby which is hydrologically similar? If so, let's use that data to do an analysis of the flood event. If this is a donor site, if this is a site that we're going to use to make predictions from, we'll then estimate the model parameters, and we'll use the ratio between those parameters at the donor site and our subject sites to get appropriate values for our subject, and then we'll get from that best estimates of the parameters to use in prediction. If we don't have data at a suitable donor site, we can't use this donor method. We have to go around here and we get our best estimates from national or regional analyses of parameters. This approach is based on a very comprehensive and detailed data set, and it's not possible to replicate the approach everywhere because we don't have necessarily enough input. However, the overall outline of the approach is usable, and there are elements of this that we're going to use for the Philippines flood estimation. In the UK situation, we're able not only to predict discharge, but also say something about the shape of the hydrograph, and that's based on a range of catchment descriptors. We have the catchment area in kilometres squared. We have the mean annual rainfall, expressed here as the standard annual average rainfall in millimetres. We have an index of flood attenuation because of reservoirs or lakes in the catchment, which goes from 0 if there's no lakes or reservoirs up to 1 if the catchment drains entirely into a reservoir. We have a base flow index. We have a soil moisture deficit term called prop wet, which looks at how often the soil is in moisture deficit, and therefore there's capacity for the soil to take up rainwater. We have the mean catchment slope. We have a floodplain extent term. We have a precipitation ratio telling us something about how extreme the precipitation in that region is in terms of the 100-year versus the 2-year rainfall event. We have a median one-day rainfall, and we have an evaporation term. And a couple of other terms not in this table, which you see in the equations. We have a drainage path length, and we have an urban extent term, which is an important land use term. Just to give you a quick example then, here is an estimate of how you calculate these parameters for a river called the River Leven at Leven Bridge. From the CD, or now online, you would get the descriptors of that catchment. So base flow index 0.381, proportion wet 0.34, drainage path length 25.49, slope 74.5 metres per kilometre, and a very low urban extent of 1% of the catchment being urbanised. From that, we can predict the maximum soil moisture depth using this equation, 309 millimetres, the time to peak of the hydrograph that we're designing. Again, use this quite complicated equation. The answer is 10.2 hours. Base flow lag, put numbers into the equation, we get 55 hours. Base flow recharge coefficient, put numbers in there, we get an answer of 0.9. So this is all based on very detailed and extensive analyses that have been done by other people, which is always nice. We can't do that in the Philippines, so we're going to use a slightly simpler approach to begin with, because we just don't have all of these parameters available. In the UK, there's been a bit of a history of ever more complicated equations. When people started doing this, they just used catchment area. And back in the 1960s, a couple of different approaches were developed, both of which predicted the mean annual flood based on catchment area. And you can see they came up with a statistical R-squared of 0.6 from 57 sites, an equation with an exponent of 0.74. At the same time, they also tried adding in rainfall, and the R-squared improved from 0.6 to 0.92. In other words, you get much better prediction if you also look at the variation of rainfall across the country, which is quite significant in the UK, ranging from about 3 metres per year in some of the wetter areas to about 0.7 metres per year in some of the drier parts of the country. In 1975, the first flood studies report was produced, which was again predicting the mean annual flood and doing that based upon some additional parameters: catchment area, the drainage density, stream frequency in the catchment, the slope of the river as a whole, a soil infiltration capacity term, a term that is based on the rainfall minus the soil moisture deficit, and an estimate of the amount of lake and reservoir storage in the catchment. Now 532 catchments were included, or 532 data recording stations were included, with an R-squared of 0.9, so quite a reliable equation. By 1999 and through to the present, the approach has moved from using the mean annual flood to using the median annual flood, QMed. Similar terms are used: catchment area, rainfall, the flood attenuation due to reservoirs and lakes term, a term that is related to base flow, and initially they used this term res host, and then it was very much an empirical term that didn't have a strong physical meaning, so it's been moved out of more recent equations and replaced by more detailed consideration of the rainfall and the soil moisture properties of the catchment. Up to 728 sites were being used by 1999, and again we get an overall R-squared of over 0.9, so quite a high coefficient of determination for these predictive equations. So that's the UK approach, and what we're going to look at in the next lecture for the Philippines is going back to these more simple approaches, and let's consider whether we can get acceptable estimates of flood magnitude from catchment area and rainfall, because if we can start to use those in design and in predicting flood magnitudes. So that's what we'll next time. Thank you for now.